So, welcome. This is the Pymol tutorial number 2, and we're going to be talking about making selections and using different commands that are available in Pymol. Before we start, just as a quick recap on last week, some of the basic navigation functions. These are just the essential ways in which we can move around in Pymol. So we have the fetch command, which we can use to bring up a PDB of choice, and that can bring up our PDB here. I'm just going through some of the viewing commands quite quickly. We can left click anywhere that we choose, and in accordance with what we have down on the bottom right of the screen here, this residue, this selection criteria, we can select different things such as individual atoms, residues, chains, and once you've made a selection you can deselect by clicking in black space and reselecting somewhere else, or you can select another thing in order to add to that previous selection. We can middle click anywhere on the protein or the molecule of interest in order to center our camera around where we've clicked. We can middle wheel in order to do Z clipping, to clip out the Z plane, which means that we can focus in on various areas quite easily. We can right click to open up a menu that has specific options for the specific thing that you have clicked on. We can left click and drag, which does our basic rotation. We can middle click and drag, which does our basic translation, and we can right click and drag, which does zoom. Now all of these are camera options. This is the camera rotate and a camera translate and a camera zoom. I'll bring your attention also then to the sequence view, which we click on the little S button down the bottom right. That gives us our sequence, and by selecting your particular criteria that you want to select, we can identify particular selections. Selections appear on the right in brackets, whereas objects appear on the right without brackets, and you can use your middle click on any of the objects to center your view around the object, and you can middle click on the selections in order to center your view around the selections, and of course you can middle click on residues in the sequence view in order to center your view around those. There is also an editing mode. So down here in the bottom right where it says viewing here, if you click anywhere in this slab you can alternate between the viewing and the editing mode. In the editing mode, let's get rid of this for a moment. If we left click somewhere, that was a bad example, so let me left click here, we can make this little pick, which is a little sphere here, and if we left click elsewhere we can make another pick and it will measure a distance for us, and if we left click again we make another pick and then it gives us an angle, and if we left click again we can make another pick and it will give us a dihedral. If we middle click anywhere, we again move our view in the same way that we would have been if we were in the viewing mode. If we right click, we again open a menu, the same as if we were in the viewing mode. Left click and drag rotates, right click and drag rotates, middle click and drag translates, and right click and drag zooms, so that's all the same as the viewing options. However, when you're in the editing mode, there's some other things that you can do by holding shift and then middle, left or right. For example, if you have two objects open and you hold down shift and then right click and drag, you can rotate one object independent of the other object. And again, if you middle click and drag, you can translate one object independent of the other object, and if you right click and drag, you can translate through the Z plane one object in relation to the other object. If we show our representation as sticks, we can also do some further things in the viewing mode, in the editing mode, sorry. So if we just come and have a look down here, we can use control, left click and drag, and this actually moves atoms around in space. You want to be very careful about doing that because obviously these have very specific angles and distances. What we can also do is control and right click, and that brings up a little angle modifying tool, and while holding control I can now left click on the thing on one side of the object and I can twizzle around that particular bond, or I can right click on the other side of that of the bond and move the other side of the object. If you're working on an Apple Mac, and you try and do this, you can't do the left click afterwards. So what you need to do is do the right click and drag. And you'll notice that here I have one of these angle modification little widgets on one side of the bond, but if I right click and drag on the other side of the bond, then I get the other guy. So this is how it would work on a Mac. You have to manually choose between those two sides. And that is it for our recap. Feel free to barge in with any questions, and this time I also have the messages board open, which I'd forgotten to do last time, so I can get your messages. So that brings us on to selecting things in Pymol. So first of all, there is a nice page here, which is this selection algebra page in Pymol, on the Pymol wiki, sorry. And this goes through a whole bunch of different ways in which you can type in various commands and get various different options. So if ever you're confused about what kind of selections are available to you, you can go through this and have a good look. And you can see there are a lot of different things you can do, and there's also a bunch of different examples down here at the bottom as well, which are worth looking through. So you have that link there. Let's get in a model to have a look at here, and let's just say as sticks, so that we have all of our sticks here. Okay, so if you're on residue, so in fact it doesn't really matter what you're on, but if you right click on any particular atom, now it's obviously selected the entire residue here because that's what we have as our selection nomenclature down here, but also Pymol talks to us and tells us here what we've just done, and it says I've clicked on, and then it gives us this nomenclature here with these slashes involved in it, where it's /2chb, which as you can see is the object here that I loaded in, and then it's a /d, a /g, and then asp7 and the carbon beta. Now I think last week I showed you the PDB file, and what each of these different portions in between the slashes is referring to are different aspects of that PDB file. So the first one is just the object, so this is the actual PDB file itself that we've loaded in. Between the next two slashes you get the segment identifier. Now the segment identifier isn't widely known about outside of the context of using PDBs quite a lot, but basically this is a 4-character identifier on the far right hand side of the atom list, which you can use to classify different aspects or different parts of your molecule. Then you have the chain identifier, so here that's G. Then you have the amino acid type, ASP, the amino acid position, number 7, and the atom that I clicked on, carbon beta. So what I can actually do is if I deselect, reselect somewhere else, and I type in the word select, and I copy that selection that I'd made here, and turn on my selection here, you can see that I've reselected that atom that I had initially clicked on, as it has a little pink box around it. Now what we can also do is, rather than, if we don't want to have the entire atom here, maybe we just want to look at segment D, for example, I can say select /2chb/d, and that selects for me the whole of chain D. You can probably see where this is going. What I could also do is, well, segment D and chain G are actually the exact same selection here. So what I could then do is say, well, I actually specifically want to have ASP7 of chain G in the object 2CHB. And now you can see there I have just selected that particular residue. And again, I could go further and just ask for carbon beta. And so here are a bunch of different examples how we can select a molecular object, the chain, the residue, and the atom, using this slash criteria here. Now, one caveat of how to use the slashes is that the number of slashes are the important part. not anything else. So for example, if I wanted to select all of the prolines that are within all objects, I could just put // pro, and now you can see that I've selected all of the prolines there. I don't know if that's particularly, it's hard to see these pink boxes sometimes. I hope that's coming through. Or of course I could just select the carbon alphas of each of all prolines, and now you can see here that we have these carbon alphas selected. Now this slash criteria is very nice in the way that if I click on something, it automatically tells me what that selection is, but it's not very intuitive, and you need to make sure that you've typed in the right amount of slashes in order to make that work. So there's actually a second bunch of selection criteria which doesn't use the slashes and instead uses a more intuitive written form, and it looks a bit like this, but then you can also abbreviate it to look a bit more like this. So what we can do here is just ignore the slashes, and we can say, well, select the object 2CHB. That's nice and easy. And then we can just write something like and chain. I mean, it very specifically has to be and chain. So if we can say select object 2CHB and chain D, and now it's only going to select chain D for us. Now if we've only got object 2CHB, we can just say select chain D, and it selects chain D for us. We can also select particular residues using this resi. So for example, I can say select resi 5, and now what it will have done, you put it again, it's difficult to see there, let me just change them all into magenta so they stand out a bit. So now you can see I've selected residue 5 on each of the chains. The only caveat with this is that you need to put the larger thing first. So if we want to have chain D and residue 5, we need to start with chain D. You can't do residue 5 and chain D. You need to say residue chain D and residue 5. So there's residue 5 over there. Basically here you're using and as in the same aspect that you're using the slash, except that you don't need to have the right amount of ands as you would need to have the right amount of slashes in order to make your selection. You can also select ranges by putting a dash in between your residue numbers, for example. So here we can say that we want to just take residues 10 to 12, and here we have residues 10 to 12 selected. You can, instead of using a slash, you can put a plus symbol, and what this does, this will obviously miss out residue 11. So here we'll just be selecting residue 10 and residue 12, and you can see that now residue 11 is no longer made in our selection. So the word and you can replace with an ampersand, and the word chain you can replace with C dot, and res I, which is the numerical residue selector, you can replace with I, and then the name, which is the atom name selector, you can replace with n dot. As you can see down here, you've got the segment, chain, residue name, residue number, residue name, and residue atom. And as I said previously, you can use the ampersand here to make subdivisions of your larger things into your smaller objects that you want to select. Yeah, you can use not in replacement of the ampersand, of the exclamation mark there. So for example here, if we use this full selection criteria here, we can select these two residues, but you can see that the carbon alpha, for whatever reason, I've not selected in these two instances, because here I've said that I do not want to select them. And you can use the plus symbol in order to add multiple selections. Now there are a few caveats to using this that I should point out. One, selection criteria here, and that's because I'm trying to use the AND to say that I want to have residue 4 and residue 7, which might intuitively sound like a smart thing to be doing, but you've got to remember that the AND symbol here is always a subdivision of the previous thing, and obviously there's no residue 7 which exists within residue 4, so that will fail. I think some of this is some Python related nomenclature here, so the bar symbol is an OR, but there's no real necessity to have an OR when you're making these selections in Pymol. So really the pipe symbol and the plus symbol are equal. Now I'd just like to point out these two selections here, where essentially they look very similar. We're using the plus symbol. What this first one does, if you have a space and a plus symbol and a space, this makes a brand new selection starting from the root of the molecule. So if I make this selection here, let's see, let's just try and make them something bright to stand out. So what I've done here is I've selected chain D and residue number 4, but then I've also selected all residues that are number 7. So you can see here I've got my residues in yellow. However, if I use this one here, where there are no spaces around the AND, around the plus symbol, sorry, and I haven't put in that I'm requiring a new numerical identifier here, then this selection here will keep this second part of the selection tied in with the first part of the selection, and therefore all that I will have done is selected residues 4 and residue 7, which you can see here and here, and no other residues are selected. So this really is the nuts and bolts of the entire tutorial. Of course, I can talk about it in great length, which I am going to be doing, but of course the more that you have a go at using these, the better, and getting used to selecting your chains or selecting your residues. So let's have a quick example. We will first of all, we're going to reinitialize our session. We're going to use this fetch command, and I'm going to specifically fetch a PDB file rather than a CIF file. I'm going to remove anything that is not a polymer, which is a protein, and then I'm going to color everything grey, make my background white, and then I'm going to orient the view around my molecule. So we can do that and have something that looks like this. Sorry, I should tell you this is an example. Your boss, whoever that might be, may even be yourself, is interested in looking at areas on a protein that we can do some kind of NHS ester modification. And therefore what we want to do is we want to identify all of our primary amines, and this is a method to do that quite easily. So really we're looking at lysines and the N-terminus. So first of all what we want to do is select all the lysines that are on chain D. Sorry, I should put a little hash there because that is a comment, as that one there is also a comment. So what we can do is we can use our select command, and we're going to, if you type a word after the word select and then a comma, what we do here is that we make a selection called whatever we've typed here. So this could be anything we want. But what we're going to have is, so we're going to create a selection that's called lysines, and that's followed by the comma, and then we have that selection nomenclature that we're talking about up here, where this is going to be chain D and residues that are called lysine. So we can make this selection, and now all of the lysines you can see are selected here on chain D, and what we have now also is this lysines selection rather than our temporary seller selection that we would normally work with. Now that we have the lysine selection, we can call back that selection and start asking it to do other things. So for example, we can't see any of the bonds or the atoms here at all, so let's have a look at, let's use show sticks. and say show sticks on lysines, and that brings our sticks in. And then we want to maybe show a sphere around the primary amines in a lysine. That's going to be the atom name NZ, which you can find out from the PDB if you have a look at that. So that then puts a sphere on the end of all of our lysines, and then we can colour those blue. And now we have identified all of our potential linkage points on our protein, except for our N-terminus. So here we can make some more selections. So here I'm just making a selection name called the N-terminal residue, because you can see that's a name, it's got a comma afterwards. And here I'm going to make a selection. This is something I haven't talked about, but BR is by residue. So I'm making a selection by the residue, and I'm going to find the very first atom on chain D, and then I want to make a subdivision of that, which is going to be the atom name N. So that's a little bit of a complicated one, perhaps. As a matter of fact, that last part of that doesn't actually work anyway. So this is the N residue that I've got, so then I can say show the sticks of the N-terminal residue. Here it is over here. And then I can say for the N-terminal residue, I want you to pick the nitrogen on that, the backbone nitrogen, and put a sphere there, and then make that blue. And there we are, there's all of our potential linkage points there. And then we can make it look a bit fancy, as people like to do, by putting a surface on it and adding a little transparency to that surface. And then we can have a look at those locations with respect to their solvent accessibility, and make sure that they're not too buried, and then make some kind of judgment. In a very, very similar example, we can try and view all of the hydrogen bonding potentials in our protein. And potential is probably a bad word to be using, because it's not a potential. What we're just going to do here is look at the donators and the acceptors. So essentially, the ionics and the hydrogen bonding guys. So first of all, let's look at the ionic interactions. So here we can select chain D and residues lysine plus arginine, and you can see there's no space around the arginine, so this is all one selection, which is a subdivision of that D selection there. So here are our lysines and our arginines. Show sticks. Sorry, that was probably didn't need that first line there, because actually what we want to do is look at the lysines, the arginines, the aspartates and the glutamates. We're going to colour blue our lysines and our arginines, but not any of their backbone or side chain atoms, except for the ones that we're interested in. And it's a little bit of a cheat as well, that is, but I'm sure that you get the picture. So here we're colouring part of the molecule red, part of the molecule blue, and again we can show our surface and set some transparency, and again now we can see where all of the ionic interactions are on our molecule. And similarly, what we can do is look for these hydrogen bond acceptors and donors by using this donator and acceptor nomenclature, and maybe using some different colours, and we can see that we can bring those out. So you can see that I've been using some commands which I haven't talked about, such as these donators and these acceptors, and using this by residue. So let's just talk about we've talked about the basic selections of parts of the PDB, going through the chains, residues, residue numbers, etc. But there's also a bunch of shortcut selections that you can make. So let's just bring our molecule back in again. What I've done this time is I've reinitialized I've fetched my protein of interest as a PDB file. This time, in order to do some colouring on it, I've used this util CBC, and CBC, in my head I have that as colour by chain, so each different chain is coloured in a different colour. If you do this, you can see that we lose all of the atomic colourings on our atoms here, but if we use util CNC straight afterwards, that brings back our blue nitrogens and our red oxygens. So the combination of util CBC to give different coloured chains and util CNC in order to give different atom colours is a nice combination. And of course, orient is a nice command to use whenever you're getting lost in order to bring whatever you have selected over here back into the foreground. So there are a bunch of different groups. For example, we can select everything. You can select nothing, which deselects everything. You can select all the water residues by saying select residues with the residue name instead of this being lysine or arginine or whatever. You can just have HOH, and that will select all of our water atoms for us. We can select just the het atoms. Now again, if you remember from last week when we looked at the PDB, there are lines where on the far left hand side you have the word atom, which are all of your protein lines, and then all non-protein lines, and I think non-nucleic acid lines start with the identifier het atom, and so we can use that, and that also brings our organic molecules as well as our waters and our salts. You can then play around with this selection nomenclature that I described earlier, so we can say, well, select the het atoms and not the residues water. So now it's only going to select organic and inorganic atoms. You can just select organics by themselves by saying select organic, and that gives us then just your small molecules, and so on, various other ways of doing it. If you only want to select the polymer, which is always just the protein or nucleic acid, you can say select polymer, and you can see that now our organics are not selected. You can, if you've got something that has both protein and DNA in or RNA in the model, we can choose between those. I've talked about selecting that, and selecting solvent is basically the same as saying selecting water. We can use SS in order to select specific secondary structure. For example, we can just select our helices, or we can just select our sheets. Now, you'd think that what you could do if you were interested in looking at some loops is say select SSL. That unfortunately doesn't give you anything, but because we know our selection nomenclature, what we can do is we can say select our protein and not secondary structure H and S, and then that will give us all of our loop regions. So maybe if you're interested in how loops are interacting with various things, you can do that. You're interested in a protein sequence, perhaps, that someone has given you, and you know it's somewhere inside your PDB, but you don't quite know where it is. Well, here you can use a selection criteria called PepSec, which is peptide sequence, and so, for example, we can select the peptide sequence teak in chain D, and that shows us here that selection. And again, we could go over to our sequencing view here, and whatever you've got selected always appears as a thick coloured line in the scrolling bar, so you can see that somewhere in this yellow section is that teak that we've asked for, and you can abbreviate pep sequence to PS dot. Let's orient again. You can select side chains. You can type the word side chain, or you can just type the word the SC dot abbreviation for side chain, and this selects all of our side chains for us. You can select just the backbone atoms, which then just selects backbones. This is hydrogen bond donors, hydrogen bond acceptors, and then you can make expansions. So this is a bit like the opposite of using the ampersand in order to make a subdivision of chain D with the subdivision of residue I. What you can do here is you can choose a particular atom, for example, and then you can expand that selection back up to either the molecule or the chain or the residue. And I used that example up here. So let's just see what happens if I didn't use this. If I say select the N-terminal residue and I'm going to delete BR. So I'm just going to say select the N-terminal residue, which is going to be the first on chain D. Now what happens there is that only selects one atom, right? Because that is the first. This is what the command first does. Is it selects the first atom in that selection. But if I put by residue, what I'm then going to do is expand that selection up to the residue. What I could do is say by chain, and that would expand it to the chain, or I could say by molecule and expand that back. Oh, that should have worked. No, it would be by object, not by molecule there that I'd want. And let me just see. You can type by object, but of course there's no need to ever do that because you could just select the object. But these selectors to expand from a smaller selection kind of can come into their own in other ways later on. Now that's all very interesting, isn't it? Look, you can go around and you can make all these selections, but what's the point in making all these selections? How is it going to be useful for you? Well, once you get your head around this selection nomenclature, then the exact same way that you can make a selection up here, you can also tie that straight into a command. So instead of starting your command with the word select, you can start it with something else. So, for example, we can use here, I think last week I told you that you can have this show, which adds a representation, or we can go to show as, which then replaces a representation. Well, we can just type as cartoon and then have our selection criteria that we've been discussing. So we can say as cartoon all. Oh, let me get rid of that. There we go. And that puts everything into a cartoon. And then, as I said before, show adds a representation rather than replaces a representation. So here I'm going to say show sticks side chains, and that puts all of my side chains on there. Now you can see that the side chain does not include your carbon alpha atom, which means that you end up getting all these ghostly side chains in space, which obviously looks a little bit rubbish. So what we can do is say show the side chain and atom names carbon alpha, and then now that makes it all look a little bit better, except for the fact that prolines, because of course the nitrogen of a proline is part of the backbone atom, and we haven't selected those. So we're going to say show the sticks of the side chain plus all the carbon alphas, and then plus prolines and only their nitrogen atoms of their backbone. And now we get a nice representation of our sticks and our cartoons. For example, again, using our selection nomenclature, which we've been discussing here, secondary structure hydrogen, we can just color it red rather than selecting it and then coloring it red. We can just say color red all of the helices. We can maybe show NB, which is non-bonded representation, all of our solvent. So now all of our solvent come up as little spheres here. Maybe we don't want the solvent, we can use the keyword remove here to remove all of our solvent. And our lines, our organic molecules, maybe we will want to have those specifically as lines. There they are, that's good. And then we can zoom to our first organic. If we did it, and this is by molecule of our first organic, if we're again going back to using this kind of expansion here, if we didn't have the bimolecule on there, the first organic would be the first atom of that organic. But what we've done is we've expanded that selection by using BM, so now we can see, we can center the view around the entire organic molecule. We can use the keyword dist, and we can give our selection a name. So we're going to make a distance called temp, and we're going to select a distance which is on chain D, residue 4, carbon alpha atom. And then we've got another comma, so this is one selection for the distance, and then this is the second selection for the distance, where we're going to have chain E and residue 4 and the carbon alpha. And if we do all of this, we've then made a distance selection here between two atoms of choice in our molecule. And this is obviously without having to pick these atoms by hand, which would be our only option if we were going to go and use the measurement wizard, which we looked at yesterday. You've got to be careful with this, because you need to make sure that you're picking individual atoms in your selection here. If you don't pick individual atoms, you can end up with something that looks quite ridiculous and is entirely unuseful, as what this is doing is measuring all atoms in this selection versus all atoms in this selection. What is quite a useful command is extract. So here we can extract an object. We're going to call that object chain F, because this is before the comma, and then our selection after the comma is what we're going to extract. So we're going to extract chain F. And here now, chain F is an independent object which we can add and remove. And now that we have that, for example, we might want to delete it. Obviously, I should also just quickly point this out, because what we've done is we've extracted chain F as an object. That means that now when we're inside the editing mode, we can move this this object independently from the other objects, so long as you're inside the editing mode. But now that we've subdivided that from our current object, we can also just delete that object, and that object is gone. Now, this is just a few of the different commands here that I've shown. There is this command reference here. I don't even think that this is all of the commands, but this is a fair few of the commands here. And let's just see, for example, you can click on one of those commands and it gives you all of the different syntaxes that you can use and the different options that you have there for each of those commands. So this is just an example of writing out those commands. So what we can do is reinitialize our session. We can fetch our PDB, orient around it. That's maybe not necessary. We can remove the solvent and the inorganic stuff, because maybe we're not interested in that. We can color it all grey. We can make our helices into fire brick red. We can show sticks for the peptide sequence teak, and then we can color it black. We can make our background white, which is always advisable. We can zoom into this this teak section that we found at a distance of 5 angstroms from the camera. We can make sure that all of our atoms are the correct color by using util CNC. We can measure a distance between two atom points. You can see here I've used the slash nomenclature rather than the and nomenclature. And then we can color the dashes on that distance into magenta. And Pymol obviously does that very, very quickly. So you can see that's not particularly difficult, and maybe this is this could be an interesting measurement for some work that you want to do. For whatever reason, you might want to also extract a ligand. I don't quite know why this is here, but might as well do it. So here we are, we've extracted our ligand, and now maybe what we can do is we want to change the shape and the position of it in a slightly different way, or whatever it is that you need to be doing inside Pymol. Some other examples here. Here we're going to start the session again, bring in our protein of interest, remove the solvent, the inorganic. We'll make a selection called backbones, which includes the backbones, and we'll make a selection called SC, which includes the side chains and the carbon alphas and the prolines on the nitrogens. Delete side chains, that shouldn't be there. Okay. We'll colour the chains different colours. We'll show the backbone as cartoons, the side chains as sticks. We'll make it grey. We'll make the atom colours correct, make our background white, orient around our protein. Don't think we need to do that. And then we're going to make two new distance selections between our organic molecules with the side chains, and between our organic molecules and our backbones. Now mode 2 only identifies hydrogen bonds when you're using the distance function. So if you're particularly interested in hydrogen bonds, you want to use dist, make your with your distance name your first and your second selection, and then mode 2, and then we'll call them black or magenta and hide our labels. And so what we can do is stick this in. Oh, let me just make sure that worked. And here we go. So you can see what we've done here. We've got all of our chains different colors, and we've identified here in magenta organic to backbone interaction, hydrogen bond interactions, and organic to side chain interactions in black for our particular protein here. So why is it interesting to be able to do that? Well, this is essentially your first Pymol script here, and what we can do, if you have that particular set of instructions saved just into a text file like this, and you're in Windows, you can just double click on that script and it does it for you. This script has 1 NQU rather than 2 CHB. So it's a slightly different protein, but again, you can see here is our small molecule of interest, and we've identified all of the backbone and side chain interactions between that small molecule and its protein. So what you can essentially do is replace this word here, so this PDB code here, with any PDB code, and because these are generic commands, you can use this script here to generate this kind of image with any protein from any protein from the PDB. So this is one reason why all of this is hopefully going to be useful for you. And in the last few minutes, I thought I'd run through a quick exercise which uses a bunch of these different commands in order to do a particular task. Now, my boss was interested in a bunch of different coiled coil structures, and he gave me a list, and he said he wants a nice picture of these different coiled coils. So how are we going to do that? Well, first of all, we better fetch them. So here are all of those coiled coils, and you can see they come in a variety of different formats there. Now we're obviously going to make things look nice, so we're going to make the background white, make sure everything says a cartoon, which will remove the solvents, and then we want to align all of these objects together. Now, I showed you before that you can use align all to this object, but there's a command for this as well, which is just called extrafit. And extrafit also needs a selection criteria, so here we're using the atom name carbon alpha, and it needs a target, so our target is going to be 34A, and then it needs a algorithm by which to make that fitting. And I think last week I might have talked to you about align, super, CE align, and various other ones. So here we're going to use the extrafit against the carbon alphas and align them all together. Now, that doesn't look particularly great, does it? One of the reasons that it doesn't look particularly great is because actually some of these objects have got multiple coiled coils inside the same PDB. I spoke to you last week also about using type equals PDB1. And what this should do is only bring in the biologically relevant molecule rather than the asymmetric crystal component. So if we use type equals PDB1, you can see that that now looks a lot better, and then we can repeat the process. Okay, there we are. So now they're kind of all seem to be aligned together a bit better. Now when you've got multiple objects that you are comparing, sometimes it's nice to compare them like this. However, you can't really make out the individual objects there, so I just introduce you to a nice function called grid mode, so we can set the grid mode. And what this does is it puts each of our individual components into their own little window, which we can independently move around. And this way, of course, we can, now that we've aligned them all together, we can look at them a little bit better. Now this is all looking pretty good, except for this guy here. This doesn't really, this looks more like a helix than a coil. The blue object, as I remember, and this orangey browny object, they had multiple chord coils inside the asymmetric unit. This one here only had one helix inside the asymmetric unit, but we've used type equals PDB1, which should bring in the biologically relevant unit. You can see here that this particular object, the pink guy here, has got two states, and we can, because it's got two states, we can use our play button and we can play between those states, and you can see them here. So we have got our chord coil here, but they are in two different states. So what do we do about that? Well, we can use a command called split states. So let's do that. Split states on 4DZM. So now we've split that, and we've got two new objects called 4DZM01 and 02. So because we've got the two new ones, we can delete the old one. And then we can create a new object, which is a combination of 4DZM1 and 4DZM2. Now there we are. We've made our new object, but you can see that that object doesn't look particularly healthy, does it? If we say as lines to have a look at the lines, we can see that all of the atoms are in the object there. It's just that when we say as cartoon, that there's a problem has occurred here. And if I click on one of these guys, you can see that even though I'm trying to click on one atom, I'm actually somehow clicking on two atoms each time I'm doing it. Now what's happened here is that the chain identifier and the residue identifier and the residue number and the segment identifier, and basically all things that identify this atom from this atom, sorry, this residue from this residue, are identical. So when we've combined the two objects together, we've now got a merger of these two objects where the identifiers between them are identical. This is actually an important problem whenever you're going to get around to splitting objects and making new combinations of objects in Pymol. This is quite a regular issue that people come across, is that they end up smushing their molecules together. And if you were to save this and reopen it, all of the way that the PDB is constructed will be completely mushed together as well. So how do we avoid this? Let's delete this new guy here. What we need to do is one of these objects here we need to change the atomic identifiers for. And we can do that using alter. So if you use the alter command, what you're essentially doing is writing or replacing certain identifiers inside the PDB itself. So when you resave it, you'll be saving a PDB with new information in it. Now one thing that we can do is this 4-character segment identifier that I talked about. So what we can say is we're going to alter 4DZM2, and we're going to put in a new segment identifier called new 0. And if we do this and then we recreate our object, you can see that we have no longer smushed those together. So that's one way of doing it. Another way that we could do it is to say that actually we want the chain to equal B instead of the chain equaling A. So that means it would have a chain A and a chain B. And if we put those two together, you can see that that works quite well. Or what we can also do is change the residue number. So what I'm going to do here, this looks like a bit of complicated code here, but it's not too bad. What we're doing is we're going to make the resi, which is the residue number identifier, equal, well, it does get a little bit complicated here, a string which is an integer, which is the current residue identifier plus 100. So what we're basically going to do is increment the residue number by 100, and again we can do that, and we end up with residues here that are 100 larger than the previous ones. Okay, so there we are. We've got one that we liked, and now we've got these different coiled coils, and they all look pretty good. Enable all. We don't need to do that. Grid mode. I think we're already in the grid mode, but you can see that actually, if we look down the axes here, that some of these aren't quite looking particularly centered. So maybe we should use, well, we use this super alignment, and that seems to be okay. You can see it when we use extra fit here. It gives us these RMSD values for each of our fittings. So now we can compare these, and we can use extra fit again, but using a different alignment criteria. Let's bring that down, and you can see that all of the alignments seem to be a little better than they were previous. Or we can use the center of mass align. Oh, now these ones are really rubbish, so maybe our first, or at least this align one here, seem to be the best. And of course, because these are separate objects, you can go into editing mode, and if you figure that this guy here should actually be a little bit more vertical than it is, or maybe this guy here you want to tweak around, you can make some more kind of bespoke movements of those guys, and then you can hit ray, or you can type ray, and then that makes us a nice image which we can send off. So I understand I went into some quite specific details here, but I thought I'd try and highlight some of the usefulness of why it's important to have these commands. That all of those commands you can just build into scripts, which you can hopefully reuse multiple times. You can actually, if you're very interested, you can write your own Pymol RC file, which means that every time that you open up Pymol, it will iterate through a bunch of different commands that you have. Kind of useful, but also not particularly useful, because you maybe don't want to perform the same actions every single time. And that is it. Are there any questions? Oh, one question. Could you show me how to display residue ion interactions? Residue to ion interactions, are you talking about residue to metal ion interactions? Yes. I need a metal ion then, don't I? Okay, so we shall rein. We can fetch this guy. Here he is. We don't want to remove inorganic, because of course that will be removing our metal ions. So here we go. And now what we can do is we can ask for, we'll make a distance selection with a particular name. That doesn't really matter what it is. And what we can say is inorganic. Let's just put in side chains. And what this should hopefully do is just bring in any interactions between any side chains, any hydrogen bonding interactions, because we're in mode 2 here, between any side chains and any... Okay, well, we've got a few there. Now, there's actually one hidden in here. Well, there we are. I think really it's just this line here, where we're making a distance object here, and we'll just make that magenta so it's a little more clear. And then we can remove our solvent. Okay. Alright, in that case, if there are no more questions, I think we're done, and see you next week.